Good evening, class. We are looking at exam one review, chapter 2, limits and derivatives, and we're going to cover from section 2.1 to 2.8. Here's the first part covering from 2.1 to 2.3, and for 2.1, the tangent and velocity problems, 2.2, the limit of a function, and 2.3, calculating limits using the limit laws. So this is the entire chapter, and we're going to cover the first few sections. So again, just quickly, the tangent and velocity problem, the limit of a function, calculating limits using the limit laws, the precise definition, continuity, limit at infinity, derivatives and rates of change, the derivative as a function. So limits of a function, finding limits by numerical and graphical methods. Definition, this one is read, the limit of f of x as x approaches a equals L. The limit of f of x as x approaches a equals L. I want you to pay attention to these three graphs. The limit of f of x as x approaches a. From the left and right, when you look at the limits, we'll look at the one-sided limits. From both sides, we are moving towards a. Along the curve, from the left is going this way, from the right is going this way. Along the y-axis, from the left goes up, from the right comes down. And in all cases, we are moving towards this point. We never get there. That means the y-coordinate is L. Same thing for each case. So the limit exists, and the limit of f of x as x approaches a equals a. What's the difference? Over here, at a, the functional value is a. In other words, f of a equals L. At b, f of a, solid point, has y-coordinate b, which is not equal to L, therefore it makes it not continuous. At C, so you see the hole here. At C, f of A, there is a hole here. We don't have a solid point, so f of A is not even given. We say f of A is not defined. So in short, part A, f of A equals L, part B, f of A equals B, which is not equal to L, and part C, f of A is not even given, is not defined. But in each case, regardless of what happens to A, limit of f of x as x approaches A equals L. Here's the definition of HA, horizontal asymptote of a curve y equals f of x, as the equation y equals L. If the limit of f of x as x approaches negative infinity is L, or limit of f of x as x approaches infinity is L. Here's the definition of VA, vertical asymptotes. When the limit of f of x as x approaches a, or a from the left or a from the right, is positive or negative infinity, then VA, vertical asymptote, has the equation x equals a. And the limit exists if one-sided limits are identical, meaning the limit of f of x as x approaches a from the left, this means a from the left equals L. The limit of f of x as x approaches a from the right equals L. If they are identical, the limit of f of x as x approaches a does exist, and it's equal to L. If the two are the same, that means the limit of f of x as x approaches a and f of a, they have the same value, such as the very first graph, then we say the function is continuous at that point. Finding limits by numerical, graphical, and graphical method. We start with simple example. Guess the value of the limit of x minus 1 over x squared minus 1 as x approaches 1. The function f of x is this rational function, which is not defined when x equals 1. The question is, does it matter? And the answer is no, because you are not looking at x equals 1. Precisely at x equals 1, that means the functional value. You're looking to find the limit. So what would be the methodology? If you go with the numerical method, and don't ever use that unless you're asked by the question to do that method. Let's evaluate this for values of x that approach 1 but are not equal to 1. This is the key to explain the concept of a limit to everybody. This is the key, everybody. Not equal to. So what do? We look at tables. So the table below give the tables below give values of f of x for values of x less than 1 and x larger than 1. So let's look at that. For x less than 1, we pick values and we plug in. For example, 0.5. And by the way, 0.5, even 0.9 is way too far. 0.99, as you add to the number of nines, you get closer and closer to 1. And you put that into this expression. You evaluate it with a bunch of decimals, more specifically 6 decimals. These are what you get. For x larger than 1, for example, 1.5 is way too far, even 1.1 is too far. So 1.01, and as you add more to the number of zeros, and then you have to put a 1, because if you don't put any 1, it's still 1 and it's not acceptable. It's close to 1. This is the closest one. You put it into this expression, you evaluate. So if you look at the last row, this is the closest number to 1 from the left, and this is the evaluated value. This is the closest number to 1 from the right. Among the numbers that we picked, this is the answer. And I hope you can compare these two and see the limit numerical mentions that it has to be 0.5. And if you have any doubts, you can go a little bit further. Add another 9 here. This one, add another 0 in between 1 point and put 4 zeros and 1, you'll see that. Numerical. If you were to graph it, it looks like that. And I hope you remember how you graph a rational function. Number one, you have to simplify. That means if there's a common factor between the top and the bottom, you have to drop it. Otherwise, where there is a common factor, creates a hole. So the hole that you see here is created by the fact that there is a common factor between the top and the bottom. However, we are not interested in what happens at 1. Look at number 1 from the left in this branch, from the right in this branch. Both of them moves towards this hole where the y coordinate is 0.5. So they do agree. However, in reality, the best course of action is to do it algebraically, analytically, and to do so, we use the fact that we can factor this. The bottom is a squared minus b squared. As you recall, a squared minus b squared is a minus b times a plus b. X squared minus 1, or x squared minus 1 squared, or x squared minus 1 cubed is the same thing. So we take it to be x squared minus 1 squared, and it becomes x minus 1, x plus 1. We drop the common factor of x minus 1. And when you get to this point, you simply plug in. And now you see the answer is 1/2. And this is the algebraic proof that the answer is 0.5 or 1/2. So we looked at it from a numerical point of view by picking values from the left and right close to 1, graphically, and of course, analytically. Calculating limits using the limit laws. Let f of x and g of x be defined for all x over some open interval containing a. Assume that L and M are real numbers such that the limit of f of x as x approaches a is L, and limit of g of x as x approaches a equals M. Let C be a number, a constant. Then each of the following statements holds. The sum law says the limit of f of x plus g of x as x approaches a equals limit of f of x as x approaches a plus limit of g of x as x approaches a, which makes it L plus M. In other words, the limit of the sum is the sum of the limits. Difference law. The limit of the difference is the difference of the limits L minus M. Constant multiple law. If you multiply a function by C and you want to take a limit, you can take the constant out, C times N. Product law. The limit of the product is the product of the limits L times M. Quotient law. The limit of the quotient is the quotient of the limits L over M. Needless to say, as always, the denominator cannot be zero. If you're raising a function to power law, you can take the limit without the power and then raise it to power of n, L to the power of n for positive integer n. And if you're taking a root, this is called the root law. The limit of the nth power of f of x is the nth power of limit of f of x as x approaches a, or the nth root of n for all n if n is odd. So if n is odd, there is no restriction. And for n larger than or equal to 0, if n is even. And the reason is very simple, class. Remember, square root of 4 is 2. Okay. Cube root of 8 is 2. But if we go with, let's say, square root of minus 4, this is not a real number. This is 2i. But cube root of minus 8, it's minus 2, which is a real number. So when it's odd, there is no restriction, the index. When it's even, there is a restriction. Direct substitution property, this is really the synopsis, the summary of the information. A continuous function at a has the following limit value. The limit of f of x as x approaches a equals f of a. Functions with the direct substitution property are called continuous at a. And basically, every function we have studied in pre-calculus, they happen to be continuous in their entire domain, and that's the key. You should know what the domain is for each function. The squeeze theorem. If g of x is between f and h, so f of x is less than or equal to g of x less than or equal to h of x, so g is squeezed or sandwiched between these two functions. When x is near a, except possibly at a. In other words, we don't care what happens at a, we're talking about near a. So the one on the left, f of x, and the one on the right, when you take a limit of f of x as x approaches a equals limit of h of x as x approaches a equals L, then the one in the middle by the squeeze theorem has the same limit, the limit of g of x as x approaches a equals L. So those are the synopsis of what we need to know. Let's look at some graphs and let's remind everybody what this means. This means a from the left. The limit of f of x as x approaches a from the left equals L. And if limit of f of x as x approaches a from the right is L, then limit exists and it's equal to. So we are interested in finding the limit of f of x as x approaches 2. That's why we look at one-sided limits. So you find number 2 along the x-axis. So from the left side of 2, we are moving this way. As far as the curve is concerned, we are moving this way. That means we are moving towards this point. and this point has a y coordinate 3. The limit of f of x as x approaches 2 from the right. Along the x-axis, we are moving this way. Along the curve, we are in this branch, moving towards this point. The answer is the y coordinate is 1. Are these two the same? No. The limit of f of x as x approaches 2, d and e does not exist. F of 2, limit of f of x as x approaches 4, and f of 4. First and foremost, so what is f of 2? You look at a solid point, which is this point, and the answer is its y coordinate, which is 3. So we want to distinguish between limit and functional value. So, and by the way, since these two are the same, later on we discuss the continuity from the left. The function is not continuous because the limit doesn't exist, end of this. However, these two are the same, and this is limit from the left. So the terminology is that it's continuous from the left, but nevertheless, it's not continuous. What about 4? We want the limit of f of x as x approaches 4, and notice we approach 4 from the left, we approach 4 from the right, and in both cases, we are moving towards the same hole as having the same y coordinate 4. Because they are identical, the limit of f of x as x approaches 4 equals 4. But what about f of 4? You look for a solid point, it does not exist, so f of 4 is undefined. The terminology is undefined versus does not exist, okay? Don't mix them up. Now, it's really not that big of a deal, but in case. Now, what it means is that at 4, we do have a limit of f of x as x approaches 4. At 4, we don't have a functional value. So nevertheless, it makes this function discontinuous at 2 as well as 4. But the difference is 2 is a jump and we can't fix it. 4 is a hole. And if we redefine f of 4 to be equal to the limit value, it is fixed up and it works. That's the difference between the two. Here's the graph. The limit of r of x as x approaches 2. So I hope you see that as we approach 2 from the left or right makes no difference. In both cases, it's going down to negative infinity. For limit of r of x as x approaches 5, approaching from the left or approaching from the right, both of them makes no difference, will take us to infinity. But negative 3 is a different story. And please understand this, negative 3 from the left, okay? So to the left of it, like from negative 4, and you get closer and closer to negative 3. From the right, that means from negative 2, you get closer and closer. So negative 3 from the left means we are moving this way. And as we getting closer and closer to negative 3, this goes down to negative infinity. If we approach it from the right, it's moving this way to positive infinity. But no matter what, according to the definition of a VA, which says if the limit of f of x when x approaches a either way from the left or right, it's either infinity or negative infinity, x equals a. So in this case, x equals 2. In this case, x equals 5. In these two cases, they refer to x equals negative 3 as VA, vertical asymptotes. So it's pretty straightforward, everybody. How do we find the limits algebraically? Just plug in and observe. That's all. So what happens when you plug in? It may give you a number, it works out, and you're done. It may give you a 0 over some number other than 0, which is 0, and you're done. It may give you some number over 0, and the only thing you want to be careful of is it going to be infinity or negative infinity, because we used to say numbers divided by 0, they're undefined, but now actually we figure out whether they're positive or negative infinity. However, in calculus, most of the time, we get to a format called indeterminate form, such as 0 over 0, infinity over infinity, infinity minus infinity, 0 to the power of infinity, and things of that nature. There are formats that are indeterminate. So indeterminate, in short, means more work. It means use your algebraic techniques to figure out what to do, and that's what we are going to look at. We want to find the following limits. The limit of the square root of x plus 4 minus 2 over x as x approaches you. We plug in. 0 gives us square root of 4, 2 minus 2 over 0, which is 0 over 0. And as you recall, this means indeterminate. So when it's 0 over 0, you have to figure out a technique that will fix the problem. Whenever you have a square root, the technique is the conjugate, okay? The conjugate of a minus b is a plus b. So the conjugate of this piece is the same thing with a plus sign. So we are going to multiply and divide by it. By the way, you can't say I'm going to multiply by it only. You can only multiply by number 1. And this expression is equal to number 1. And that's fine. You can't just multiply by that. Now, the conjugate of a minus b is a plus b, and their product is a squared minus b squared. Recall, a squared minus b squared was a minus b times a plus b, and so if you multiply these two, you get a squared minus b squared. So that's extremely important to pay attention to. So what do we do? Very simple. As far as the denominator is concerned, class, remember, when we have 0 over 0, it's the 0 in the denominator that creates a problem. We never multiply this through. We never distribute. We keep the denominator as x times this in a parenthesis. When we multiply these two, a minus b, a plus b, we get a squared. That means the square root of x plus 4 squared minus b squared, that means 2 squared. So we get x plus 4 minus 4 in the numerator. By the way, I want to remind you that when you have minus 2 squared, the answer is positive 4. Minus 2 squared is minus 4 because the negative is outside. 4 and negative 4 cancel each other. X and X cancel each other. And now if I plug in 0 here, I get 4, comes out as 2. 2 and 2 is 4. The final answer is 1/4. So this is the numerical method to do the job. We want to take the limit of x plus 2 over x plus 3 as x approaches negative 3 from the right, and the same thing as x approaches negative 3 from the left. I hope you realize that if you just ignore from the right and left, the numerator is negative 1 and the denominator is 0 in both. Now, first I want to discuss the numerator. The numerator in both cases makes no difference. It's very close to negative 1. Please understand. Negative 3 from the right or left when added to 2, it's very close to negative 1. Now, because this is from the right, this is like negative 0.9999, and this is from the left, so it's negative 1.0001. But the reason the bottom is important, because when you look at every number, both sides have the same sign. As, for example, if I have number 5, the left side and the right side are both positive. For example, 4.9 over here, 5.1. If I look at negative 5, the left side, negative 5.1, and the right side, negative 4.9. Both of them are negative. The only number that one side is negative and the other side is positive is 0. And the reason you need to figure it out, because now this is, if you have a number divided by 0, it goes to infinity, but you have to know it's negative or positive infinity. So we are going to go with negative 3 from the right. And to be able to do that properly, we actually pick a number to the right of negative 3, like negative 2, let's say 0.9 plus 3 becomes positive 0.1. So it's negative 1 over 0 from the right. Whereas here, negative 3 from the left is like negative 3.1 plus 3, which makes it negative 0.1. So it's 0 from the left. The difference is now negative over positive is negative infinity, but here negative 1 over negative is positive infinity. So negative infinity, positive infinity. That's the easy process to figure out positive or negative. Now, if you plug in 4, it ends up being 0 over 0. But in general, anytime you have a rational expression, anyways, it's a good practice to simplify it. By that, I mean we put it in its lowest term. As always, it's the 0 in the denominator that creates a problem. Because x is approaching 4, everybody, pay attention to this. This will help you with the factoring. There must be a factor of x minus 4. If x approaches 5, there must be a factor of x minus 5. If x is approaching negative 2, there must be a factor of x plus 2. Okay? just to help you with the factor. Of course, when you want to factor easily, the top, you just take out the x. The bottom, you want two numbers. The product is -4. The sum is -3, which makes it -4 and +1. But as I mentioned, this will help you see that this is one fact. These two cancel each other, you're left with the rest of it. And if you plug in 4, you get 4/5 as the final answer. The limit of the square root of 1 plus h minus 1 over h as h approaches 0. Again, if you plug in 0, what happens? This becomes 1, comes out as 1. 1 minus 1 is 0 over 0. So the answer is 0 over 0 in determinate form. And therefore, we are going to figure out a technique to fix the problem. We've already discussed when we have a square root, the technique is to multiply by its conjugate. Remember, a minus b becomes a plus b. The same thing plus 1, and you put the same thing in the denominator. Don't forget, it is important to have the same thing at top and the bottom in order for this to be 1. Otherwise, it's not acceptable. And when you do that, you keep this intact. And now the numerator, you just use a minus b, a plus b. It's very straightforward, everybody. So now, again, remember, a minus b times a plus b. Okay, it's a squared minus b squared. And we are going to use the same thing here. And so I'm going to write square root of 1 plus h squared minus 1 squared for the numerator. And we never touch the denominator because h is approaching 0. That's the problem we want to get rid of. And so 1 plus h comes out, minus 1, 1 and -1 cancel each other. H cancels out the h. And if you plug in, this becomes 1 and 1 is 2. The answer is 1/2. So again, pretty straightforward, everybody. So you can see 0 over 0 can become 0, can become infinity, can become any number in between. You have to work it out. In this case, we've got different numbers. Okay. All right. What happens in this case? We plug in first. So if we plug in, everyone, this becomes 0, but the numerator is 3. This becomes 6 squared or 36 minus 7 times 6 is minus 42 plus 12. The numerator is 3. The denominator adds up to 3 over 6, and it makes it 1/2. So it just works out. This is a complex fraction. If you plug in 3, 1/3 minus 1/3 is 0, x minus 3 is 3 minus 3 is 0, you get 0 over 0. So what is the technique? You are dealing with a complex fraction, everybody. To fix that, you use LCD to go from a complex fraction to a simple fraction. And you notice that there are two fractions here, 1/3 and 1 over x. The LCD is 3x. You're going to multiply and divide by 3x. When we do that, again, remember the denominator, x is approaching 3, which means x minus 3 is a problem. You don't do anything here. You keep this as a product. So you distribute that 3x times 1/3 is x, minus 3x times 1 over x is 3. So you get x minus 3 in the numerator, which cancels out x minus 3 in the denominator. And now you have 1 over 9 as the final answer. It's pretty straightforward. Evaluate the following limits. We reminding you of the one-sided limits. And to evaluate this, we're going to use the limit laws by cutting it into two pieces. Limit of the first piece plus 5 times the limit of the second piece as x approaches -2. So we start finding this one limit of f of x as x approaches -2. So here's number -2. We are coming to that from the left. That means here. From the right, that means here. And whether we go from the left or right, in both cases, we are moving towards the same point, which has a y coordinate 1. For g of x as x approaches -2, from the left and from the right, we are moving towards this point, and this point has a y coordinate -1. It's a continuous function at that point. So we have, this is 1 and 5 times this one, 5 times -1. They add up to -4. What about the limit of f of x times g of x as x approaches 1? Again, the limit laws, we cut this into two pieces. And we look at each piece. Limit of f of x as x approaches 1. So this is number 1. And the left and right is moving towards the same point, resulting in y coordinate being 2. That's the limit. And of course, the function has no break. It's continuous at that. But what about the limit of g of x as x approaches 1? That doesn't exist. The question is why. Let's find out why. When we approach 1 from the left, it takes us here, which has the value -2. When we go from the right, it moves this way, moving towards this point, having the y coordinate -1, because the one-sided limits for g of x as x approaches 1 from the left and 1 from the right are not the same, then the limit of g of x as x approaches 1 does not exist. Their product doesn't exist either. Just to show you how this thing works, I'm going to go over the second method just in case, and that is finding one-sided limit for the product. So finding the limit of f of x times g of x as x approaches 1 from the left, 1 from the left for f of x left and right is the same as 2. For g is -2, the product of 2 and -2 is -4. That is from the left. Now, what about the right? Well, again, f of x, that doesn't make any difference still too. The right and left makes no difference. But for the g, from the right is -1. So the product of these two numbers, which is -2, and clearly the two are different. This is the second methodology. But to make sure we understand this concept closer, I'm going to erase my work and I'm going to look at f of -2. If you look at -2 here, f of -2, you're looking for, first of all, the f is the red or purple function. So you're looking for a solid point. We do have it. And it has a y coordinate too. G of 1, we mean the blue function. At 1, you look for a solid point, and this point has a y coordinate -2. And you can think of this as continuous from the right, in case if anybody is interested. And what about the limit of f of x over g of x? As x approaches 2, same thing, it doesn't exist. Why is that? The denominator approaches 0 while the numerator approaches a non-zero number. So when x approaches 2, use a color that makes it easy to see. So here's the left side, here's the right side. So we are moving towards this point. And for the f function, we are here. That is maybe 1.5. But for the blue function, we are here that has a value 0. So you're dividing by 0. And that can't be. If 2x is less than or equal to g of x less than or equal to x to the power of 4 minus x squared plus 2, for all x, evaluate the limit of g of x as x approaches 1. We are going to use this squeeze theorem. That means we're going to look at the left side, 2x, and find the limit as x approaches 1. It's just 2 times 1 equals 2. We're going to look at the right side. This is h of x in essence, and take a limit as x approaches 1. So this is 1 to the power of 4 minus 1 squared plus 2. And as you can see, this is 1 minus 1. They cancel each other. The answer is 2. Are these two the same? Yes. Because of this squeeze theorem, and you have to mention, the limit of g of x as x approaches 1 is 2 by the squeeze theorem. You have to mention why. And the reason is the squeeze theorem again. What is this squeeze theorem? If you can find the limit of the left side and the right side, but not the one in between, and these two have the same limit as x approaches a, the one in between, the limit of g of x as x approaches a is also the same. That's the meaning of it, and I hope everybody is okay with that. Prove that the limit of square root of x brackets 1 plus sine squared 2 power x as x approaches 0 from the right is 0. For cases like this, everybody, where sinusoidal functions are involved, there is a methodology that if you follow, you come across anything similar, you can handle it. And that is, when you want to prove that you start with sine, you know that sine is between -1 and 1. If sine of alpha is between -1 and 1, then sine of 2 pi over x is also between -1 and 1. Now you work on this and you make it look like this expression, everybody. This expression, step by step. So the first thing is to square it. Now it's important to know when you square this one, you get sine squared 2 pi over x. When you square this one, you get 1. Now it's important not to think you're going to square this and you get 1. And here's the reason. If sine is between -1 and 1, all the negative numbers, when you square them, they become positive. But remember, somewhere in between you have 0. So you have to figure out that it's between 0 and 1. So in other words, everything becomes positive except, of course, 0, which is neither positive nor negative, it's a non-negative. Okay. So it's important. If you had -5 and you had a positive, I don't know, 5, this becomes 0, this becomes 25. Because when you have 0 in between, it doesn't go away, okay? All right. Now go back to this one. We need 1. So let's add 1. If I add 1 to all sides, this becomes 1, this becomes 2, and this becomes 1 plus sine squared. So it looks like the bracket. So far, so good. What is missing? Square root of x. Let's multiply by square root of x. And remember, when you have an inequality, it flips over if you multiply it by negative. However, square root of x is always positive. And remember, x is approaching 0 from the right. So the sign cannot change. You don't have to worry about that. So you multiply everything by square root of x. And now you notice you have exactly the same thing. And now you are going to apply the squeeze theorem. All you have to do, take a limit of this piece, because this we don't know the answer. But now this one we know, and this one we know. So the limit of square root of x as x approaches 0 from the right is 0. The limit of 2 times square root of x as x approaches 0 from the right is also 0. And therefore, the limit of this expression, the limit of square root of x times 1 plus sine squared 2 pi over x as x approaches 0 from the right must be 0 by the squeeze theorem as well. That is pretty straightforward. I hope everybody is okay with that. So this is the usage of the squeeze theorem. So a quick recap. This is a known fact. So you work with this. The argument of sine can be anything, including 2 pi over x. And then you make the final expression looking like that. You look at one side of this inequality, the left side and the right side, and you prove each one results in the same value, namely 0. Find the limit of 2x plus 12 as x approaches minus 2x plus 12 over the absolute value of x plus 6 as x approaches negative 6. So we're going to look at one-sided limits. So the limit of 2x plus 12 over the absolute value of x plus 6 as x approaches negative 6 from the left. So let's remind everybody of the absolute value and what it means. The absolute value of x by definition is x if x is larger than or equal to 0, and it's negative x if x is less than 0. Please understand this doesn't mean a negative value. This means the opposite of x. Therefore, with this, that means the absolute value of x plus 6 is the same as x plus 6 is if x is larger than or equal to negative 6. And it's negative of that minus the parentheses x plus 6 if x is less than negative 6. Therefore, because negative 6 from the left means x less than minus 6, that's the meaning of it, the numerator doesn't change. The denominator, you drop the absolute value and you put a negative sign in front. However, you also notice the top, you can take the 2 out. So we take the 2 out from the top, we drop the absolute value and we put a negative sign in front because of that. These two cancel each other. We get negative 2, and the limit of negative 2 as x approaches negative 6 from the left or any other number makes no difference. The limit of a constant is itself. We work on the same thing from the right. The limit of 2x plus 12 over the absolute value of x plus 6 as x approaches negative 6, this time from the right. So we write the same thing. For the numerator, we factor out the 2. For the bottom, we are up here, so we just drop the absolute value. So the result is 2, and the limit of 2, regardless of what happens here, it's a constant, is 2. Are these two the same? No. Because one-sided limits are not the same, the limit of 2x plus 12 over the absolute value of x plus 6 as x approaches minus 6 does not exist. Why? These two are different. Now, there is a second method, and that is to simplify this expression. And based on what we just said here, this expression simplifies to x plus 12 over the absolute value of x plus 6, simplifies to 2 if x is larger than or equal to minus 6, negative 2 if x is less than minus 6, and this is the limit from the right, and the limit from the right is the same as this, a constant, and this is the limit from the left, and even this might be even easier as long as we understand what we are doing. This also proves the same thing. The limit of the expression as x approaches negative 6 does not exist because one-sided limits are not identical.